Are there any questions? What I want to know is, so I've got two discs here mounted on the same axle. It's going, as this mass falls, it's going to spin around, and this piece right here is going to go whipping around, and I want to know what is the speed of the center of mass of this object when it gets to here. So this brings in a lot of components of the chapters 9 and 10. Yeah, I think 9 and 10. So let's take it piece by piece. First off, I know this mass is going to fall, causing this thing to rotate, so rotational motion. The rate at which this is going to rotate depends upon how much rotational inertia this has. So first thing let's figure out the rotational inertia. Assume that these are discs, and this is a thin rod that just is somehow attached at that point. So first, moment of inertia of big disc, moment of inertia of little disc. We'll just start out with that. They are discs rotating about the center. What is the formula? Formula for moment of inertia of a disc.
Is the 0.5 meter the diameter radius of the smaller disc?
Yes.
Which one?
Of the smaller disc. 0.5 is the radius of the smaller disc. 1.5 is the radius of the larger disc, and 1.5 is also the length of the thin rod. So the question on the floor is, what is the formula for the moment of inertia of a disc rotating about its center? We did a disc on Monday.
1/2 r squared.
Yes. So I have 1/2 times m of the big disk times r of the big disk squared, and this is 1/2 times mass of the little disk, radius of the little disk squared. So 1/2 times, what did I say? I said 2 kilograms times 1.5 squared. This would be 1/2 times 1 times 0.5 squared. So this contraption here has 3 different masses that are all rotating. The 5 is not going to rotate. They're all going to rotate. So the way you find moment of inertia of a sort of a non-simple system is you would take the simple parts and just add them together. So this is 2.25, and in a moment, I'll ask what the units are, and this will be 0.125? Yeah, that sounds about right. What are the units? Think about what was multiplied together. What are the units of moment of inertia? Someone take the lead. It is not. It's not a single word.
Meters.
No. But I appreciate you taking a shot. What are the units of mass?
Kilogram meters. Squared.
Yeah, there we go. So we have kilogram meters squared. Kilogram meters squared. All right, so now we have this rod here. So first thing I want to do is, what is the moment of inertia of the rod if it's rotating about its center? So I'm not going to worry about the parallel axis theorem yet. So I've got a thin rod here rotating about its center. What is the moment of inertia of that? We would have dealt with that on either Monday or last Wednesday. Moment of inertia of a thin rod rotating about its center. Anyone? Gilbert?
1/12 ml squared.
And so this becomes 1/12 times my mass, which is 1 kilogram, times the length, 1.5 squared. Which is point something. I want to be kind enough. We're around 0.2.
0.1875.
0.1875 kilogram meters squared. All right, but this is not rotating about its center axis, it's rotating about this point. So instead of rotating about an axis that's pointing out like that, it's rotating about an axis that's pointing out like that, around a parallel axis. So the actual moment of inertia of the rod would be the moment of inertia of the rod about its center plus mh squared, where h is the distance we've actually moved the axis. So this is going to be the 0.1875 plus the mass of the rod times the distance we have moved it. Well, we moved the rod, or the axis, from the center of the rod to the center of the discs. So that's just the radius of the big disc plus half the length of the rod. So 1.5 plus 0.75 squared. So that's 2.25 squared somewhere around 5.2.
.25.
So the total moment of inertia of this whole rotating thing, it's gotta be, well, it's some of the small disk, some of the large disk, some of the rod. So the total moment of inertia, 2.25 plus 0.125 plus 5.25. So 7.65. Sorry, I got one knot. That's it.
And how did you describe the thing? The image?
That?
Yeah.
You mean of what's going on?
Yeah.
I've got large disc with a small disc tapped to the center and a rod sticking out the side. We've got, there we go. Not scale. Large disc, small disc. I've got a string. Attached there. I got a rod sticking out. So as that mass falls, it's gonna cause this thing to rotate. And the bar is gonna go all the way around and end up down there.
So the rod's attached to the big disc, not the little disc.
Correct.
It's kinda like what,
And it's not and it's a disc and not like a pulley.
I'm
It's like
considering, I'm making them discs because the pulley becomes more complicated.
it's like a clock, but with a lot less gears.
Yes. Well, kind of like grandfather clock, which basically has a weight pulling down, causing things to turn. With a lot less gears. All right, so step one is we found the moment of inertia of the rotating bit. Step two, we need to figure out the acceleration of the 5 kilogram mass. And this makes it like a problem like we had just done last week. Or Monday, at some point. What are the forces acting on the 5 kilogram mass?
Weight and tension.
And then the forces acting on the rotating thing. Rotating structure.
Tension,
Acting where?
like the part of the circumference that the string's attached to.
The smaller disc.
Yeah.
Yeah. And so it's critical that we recognize that the tension is acting here and not out here. So I have tension. That's really the only one we care about, but there are a couple other forces acting on it. Just from the nature of the problem.
friction.
Probably, but friction's not the force you want here.
Normal force.
Acting where?
Out.
What's causing the normal force?
The two discs touching.
Oh, okay.
Oh.
I was
The
not
rod.
considering that, but yeah, I guess.
Would be the rod and the disc.
Yeah, There is a normal force, depends on how it's actually set up, but I'm picturing that we've got it sort of sitting on it like that, so it's keeping the disc from falling, so I'm picturing that there's a normal force acting up there. And there's gonna be one other major force acting on the system. Weight. A classic. Weight's a rolling thing. Now, you could also get into rope and pulley, but really, these are not exerting any torque about the center, and ultimately, that's what's matters. That is what matters there. All right, so what is the equation of motion of the 5 kilogram mass? I know we skipped a couple steps there, but I think you can handle it. Or do we need to establish a positive direction first?
Down positive.
That would make sense. All right, what's the equation of motion?
Force 10, that would be force weight minus tension equals MA.
And for this monstrosity?
Tension plus weight minus normal.
We could, that equation is actually not gonna get us anywhere. We need a rotational equation.
They're gonna be pi somewhere in there.
Actually, no. Not yet. Not in this equation. I think pi's gonna show up in the next question. Torque, what is torque anyway? How do we find torque?
Bar cross F.
Okay. All right, the only thing I have exerting any torque is the tension. Because these two are applied at the axis of rotation, so they have the torque R is 0. So the only thing I have torque here is this force. It is perpendicular to the moment arm, because the moment arm is a vector from the axis of rotation to where the force is applied, which would be there. Since they're perpendicular, I know the torque is going to be just R times F. So I have the radius of the little disk times the tension equals remember, this equation right here comes from F equals ma. What is the torque equation?
I alpha.
So this is going to be equal to I times alpha. All right, we know RL. Let's do substitution next. So weight, we have mg, m5g, minus the tension equals m5a. And down here, we have radius of the little one times the tension equals I. We know what the value is over there. I'm just going to leave it as I for right now, but we calculated what the actual value is. And then alpha. What is the relationship between alpha and A? mathematical relationship that connects angular acceleration and the tangential acceleration. There's another factor in there. Natalie,
Over R.
say it again.
A over R.
And that R would be R would, if you recall, S equals R theta, B equals R omega, A equals R alpha. Three equations which relate linear scalar quantities to rotational scalar quantities. All right, so I know our L, I know M, I know G once we establish the planet. I know that. My two unknowns are tension and the acceleration of A. We could also, instead of using A here, we could have put R alpha instead, but out of habit, solving for A first. Let's put this on regular Earth. So I have, let's not plug numbers in yet. We're cooler than that. N5G, well, basically I need to solve for tension and then plug in. So for that second equation, I know that the tension is equal to IA over RL squared. Plug that into the first one. I have M5G minus IA over RL squared equals M5A.